In this video, we're going to be talking about the start of Chapter 9, which is an introduction to alkynes. So we've seen alkanes, we've seen alkenes, we are now talking about alkynes. Alkanes, remember, are CC single bonds. This is alkanes. We saw in an earlier chapter CC double bonds or alkenes. And now we're talking about CC triple bonds, which will be alkynes. If they occur at the end of a chain, these are called terminal alkynes. If they occur in the middle of a chain, these are called internal alkynes. So let's, for a little bit, talk about nomenclature. So we're going to take the parent chain, just like we would name an alkane or an alkene, and we're going to change the ane to an yne, where the C, triple bond C, is the lowest number position in the chain. So for instance, if we had this chain here, we have 1, 2, 3, that would be propane, but since it's an alkyne, we call this propyne. We could also call this 1-propyne or prop-1-yne. But usually when it's at the 1 position or a terminal alkyne, we don't include the 1. So this 1 would be optional here. If we have an internal alkyne, such as this, we would number it 1, 2, 3, 4. So this would be 2 to indicate the position of the alkyne, 2 bute to indicate it's 4 carbons, butyne, or bute 2-yne to indicate the position of the alkyne being at position 2. If we have multiple substituents on a chain, such as a bromo and an alkyne, we're going to prioritize the alkyne, so we put that at position 1, 2, 3. So we have a 3 bromo and a 1 alkyne. So we'd have the 3 bromo and then 1 propyne. And that 1 would be optional because if it's a terminal alkyne, we don't necessarily need to include it. And finally, if we had an internal alkyne, then we had this structure here. We are going to prioritize the alkyne, so that would be 1, 2, 3, 4, 5. So we have a 4-methyl and a 2 alkyne. So we'd have 4-methyl, 2-pentyne. So we'd prioritize the alkyne in numbering these systems and name the rest in alphabetical order as we've seen before. They have similar properties to alkanes and alkenes. So they're similar in boiling point. They're similar in density. They're similar in solubility in water. So these are, generally unsoluble in water since they are aliphatic. And they're stabilized by substitution, similar to an alkene. So we saw that an alkene is stabilized by substitution. For instance, if we had an alkyne, we had ethyne versus monosubstituted alkyne versus disubstituted alkyne. We would see that the disubstituted alkyne is more stable than the monosubstituted, which is more stable than the ethyne equivalent of an alkyne. As we know from Gen Chem, they are stronger and shorter than alkanes or alkenes. So alkanes are going to be long and weak, whereas alkynes are going to be short and strong, and then alkenes fall somewhere in the middle. And we also notice that the geometry at this carbon here is sp hybridized, which means it's 50% S and 50% P character, which makes this carbon particularly electronegative. We see that the more S character we have in a particular hybridization, the more electronegative that atom is going to be. So one of the effects of having an electronegative atom, a highly electronegative atom attached to a hydrogen, is that we see that the pKa of that hydrogen is going to be substantially lowered. So if we look at ethane versus ethene versus ethyne, and we're looking at the pKa's, we see that the pKa of this hydrogen here in ethane is 62, so very high, not very acidic at all. In ethene, it's going to be 45, and in ethyne, it's 26. Compared to water, it's still not particularly acidic. Water has a pKa of about 15, but it is acidic enough that it can be deprotonated with strong base. So if we're looking at a terminal alkyne, and we add OH minus, then this would be an acid-base equilibrium. We're going to deprotonate this H, so we'd be left with the terminal alkylidyne. That's the anionic form of the alkyne, and we'd be left with H2O. To determine whether this would proceed to the left or to the right, where the equilibrium will be favored, we'd compare the relative acidity of these two protons. In this case, the pKa of this one is about 26. The pKa of water is about 15. So we would see that the equilibrium would fall to the left. So what this tells us is that OH minus is not a strong enough base to fully deprotonate an alkyne. However, if we consider a different base, we may have a base strong enough to deprotonate an alkyne. So the base we're going to be looking at is amide. So this is usually in the form of sodium amide. And when this deprotonates the alkyne, we're left with the alkylidyne, and we generate NH3. If we compare the pKa's, again, the pKa of this proton here is about 26. The pKa of NH3, that NH3 proton, is about 36. So in this case, since the stronger acid will drive the equilibrium, we do get forward push in the equilibrium. So amide, sodium amide or potassium amide, is going to be a strong enough base to deprotonate alkynes. So when we're deprotonating alkynes, and we'll see this useful in synthesis later, when we're deprotonating alkynes, we often choose a base like sodium amide or sodium hydride to deprotonate that alkyne and push the equilibrium forward. So if we want to prepare alkynes, so now we'll look at the prep of alkynes. There's two ways we can look at this. One way is the industrial method of preparing alkynes. So if we take ethane and we do high heat, this is high meaning around 1200 degrees Celsius, this will reduce the oxidize the alkane into the alkyne, and you end up with 2H2. However, this requires extremely high heat, so this is not really relevant to a laboratory setting. In the lab, we're going to do what's a double dehydrohalogenation, so we're losing 2HX. We saw the hydrohalogenation in the generation of alkenes. So we saw that in an elimination reaction on a alkane, a hydro containing an HX moiety, will generate the alkene with an equivalent of NaX and H2O. Turns out that if we have two X's and we have two H's and we add an excess, this would have to be a stronger base because we're going to have to further deprotonate the intermediate. So we have an excess of NaNH2, and then you do an H2O workup. This will generate through this intermediate here. Sorry, that's an H. So through this intermediate here would generate the terminal alkyne, and that would, to balance this equation, plus 2NH3 plus 2NaX. When we have an arrangement like this where we have X's or we have halides on adjacent carbons, we call this a vicinal dihalide. So vicinal meaning they are on adjacent carbons to one another. This can also work with another arrangement of X. If X's are both on the same carbon, and that's the same reaction conditions, we will end up with the same external terminal alkyne. If we have both of the X's or the halides on the same carbon, we call this a geminal. Geminal like Gemini, geminal dihalide. So either a vicinal dihalide or a geminal dihalide, when exposed to a strong base and then an acid workup, will generate the alkyne. This can be done with both terminal and internal alkynes, and it will or terminal and internal dihalides, and it can generate either the terminal or the internal alkyne.